So I'm delighted to be here, although I would have been surprised fairly recently. My background's in physics. I didn't think I had much connection to do with what Ray does. And then got this interesting message. David Dalrymple is a remarkable prodigy. Ray and I have been mentoring since he was 8. And he sent a note to me saying, as far as he can tell, I believe computers are going to collapse and become part of reality. And as far as he can tell, Ray believes reality is going to collapse and become part of computers. And I think those are very accurate descriptions. And so David's question was, how do those relate? And so in the next 18 minutes, I want to do my attempt at answering his question. So these are some of the world's biggest computers. This is the Earth simulator from running the global climate. This is Livermore's blue gene that nominally folds proteins but really blows up bombs. The world's biggest computers are used to model physics. But they also fundamentally are physics. There's a lot of problems in this picture. The biggest computers need megawatts in. You have to take megawatts out. There's severe interconnect bottlenecks. Oak Ridge's blue gene is bigger than Argonne's blue gene because they have the Tennessee Valley Authority. It just doesn't scale. There's a lot that's breaking in this picture. You can see where this is going, though. This is a thin wedge of the endpoint of computing scaling. These are just corners I've been involved in. This was a computer where bits were individual nuclear spins. This is one where there are individual optical scatterers. These were all computational devices computing in exactly the way you think of as computing, but every physical degree of freedom was a computational degree of freedom, and every bit represented a single physical degree of freedom. They were completely merged. And so at that endpoint, I would argue, and we're seeing the signs of the endpoint now, computer science has done a great disservice since about 1950 forward. It's maintained this fiction that information lives in an abstract world where you can do whatever you want. But the reality is it lives in the same world we live in, and all of these things that are breaking in power consumption and programmability and interconnect that are breaking in computer scaling are trying to maintain this fiction on programs and programmers that the computers live in a different world than ours. So I'd argue there's only one scalable model of computation, and that's physics, because the computers have to be physical. So here are snap peeks at what does it look like to compute in ways that build on physics. I've been looking at that in a project to create conformal computers, computers that aren't boxes, that are just raw materials. You buy computing by the pound and you put a code on the wall, and if you need more computing, you put another code of computer or pour some more in, very literally. And so how do you program a system like that? So I'm going to just skim through peaks of it. At the lowest level, this is what microcode looks like. There's a long history to this, but the version we've now developed is a synchronous logic automata, where there's cells. Each cell does a single logic operation and operates asynchronously on tokens. And so what's so interesting about this world, unlike computer architectures today, is that space, time, state, logic are all the same thing. In computers, we saw it in slides before, memory, processing are all different stuff. But in physics, information has a density, has a speed, they're all coupled. So in this world, the distance you travel equals the time it takes to travel, equals the amount of information you store, and it equals the number of operations you can do. They're all the same resource. So here's an example of a sort. Sort's an important algorithm. In this world, sorting is linear time, because every bit of storage is a bit of processing. The picture is sorts, and the picture gets as big as you want to sort as much as you want. So that's what a low-level program looks like. That's really cartoon physics. Each of these is meant to emulate a little patch of the universe doing cartoon physics. And so what's nice about this is we're implementing this in massively parallel supercomputers, arrays of commodity microcontrollers, ASICs for designing nanostructures, but the same program runs in all those different systems because the program doesn't represent the architecture of the computer, it represents the physics. So it's the ultimate portability, since they all have to satisfy physics. Yield's great because you only have to make little cells, not big things. Power's great because you only use it where stuff's happening. Speed's great because you run at gate delay. It scales because there is no sort of boundary. And then there's a very interesting connection to the programmability of it. In physics, there's an equivalence between local and global. So when I throw the pen up, you could describe this as Newtonian mechanics, or you could say the pen is just solving the problem, minimize the action. You could take the light bouncing off of me as Maxwell's equation, or you could say the light's taking the shortest path to you. Physics is full of those equivalences between local and global. Computers don't have that because they break all the symmetries. These are a function of symmetry and conservation laws. So in this world where the computer becomes a medium, you can then program in much a similar way. So I showed you a sort done from the bottom up. Here's a top-down sort. This is a funny way to say sort. It's a global expression that's made extremal by the sort. And then for the experts, if you do what's called a primal dual decomposition, you get a message-passing algorithm that ends up sort of looking like an auction where nodes bid for variables. But then what's interesting is when you write an equation, it can represent something, but the equation itself exists in a space, the sheet of paper you're working in. And so if you make the last step and actually just map the equations physically onto the space, what it does is it derives the sort I showed you. So the sort I showed you as that picture, you can understand from the bottom up of making cells interact to sort numbers, and then you can understand it from the top down as a distributed solution to a global optimization. So I don't expect you to understand the details, but that's a peek at how you'd program a thermodynamically complex computer by making a global statement. Then the next thing we need to do is load programs. So in an operating system, there's a hand of God that reaches in and loads the program. What do you do if there's no God, if the computer is just this medium? So what I'm showing you here is we're feeding in a folding code, a little bit like protein folding, in the cells in this logic automata. Then data, that's the same data the computer used, flows through the cells, and the data takes unconfigured cells and turns them into configured one. And then the interesting thing is sorting is a very organized operation, but each cell only sees its neighbor and has no notion of time. But when they connect, you'll see a little bit of blinking as they get something to do. And then when it gets to the very end, you'll see a front propagate, which is sort of consistency. Once it gets to the end, all the cells have something to do. And so that front of consistency will propagate through, and then the whole machine turns on and starts running the sort. So that was loading a global program only by doing local interactions. So now the next step is, so far, all of that is in the world of electrons, in transistors, but you can do more than that. So here's a kind of computer. In what you'll see here, this is high-speed video. It's a few hundred, about 10 kilohertz. Those are 100-micron channels, little bubbles, and each junction is a logic gate. When one bubble comes in, it goes out to the left. When two bubbles come in, they go out both sides. It does a single Boolean operation. So this is stages in combinatorial logic. And these other videos show ring oscillators and memory. This is all the things any digital logic family does. Anybody in the Valley who's trained to do logic synthesis can design a computer here. But here, each bit transports a unit of information and also a unit of material. Here's a second example. This is tiles that interact locally, and with a local magnetic interaction, they solve a folding constraint. So there's no metrology and control system and feedback, but what they do is they make shapes. So instead of just rearranging electrons, these two things together give you the ingredients to do everything I told you, but now make it out in the physical world. And that's something we're doing in a somewhat ambitious project aiming to create life. This is with a number of partners. There's a complexity in fabrication from simple coded, from just self-assembly, stuff sticks together, to coded assembly, writing a code in a structure, to programmed assembly where there's algorithms, and ultimately life. And we can do that on nanometers with biology. You can do anything on big scales, but there's a mesoscale, microns up to millimeters, where it's really hard to make very complex things. And so taking the last few slides, what we're looking to do is re-implement all of molecular biology in engineered materials to code construction. It's called millibiology because microbiology is actually the biology of nanometers. And so since we're doing microns, we should be microbiology, but that's already taken, so we're millibiology. But we're trying to really re-implement all of biology to enlarge the material set of biology to code for construction. So in turn, that leads, and so here is an example of the CAD workflow. This is a video from Jonathan Bachrach at Makani Power. We start from a CAD file, an STL file. We find a Hamiltonian path that fills it. We decompose that into a folding string. And then what's happening is each of the local cells is trying to solve its local constraints. And it doesn't know anything about the global shape. But when they each solve all of their constraints, you make a wrench. And so we're building this is part of a whole CAD workflow, and we're building parts now that can execute that. So you code construction by writing it into a string that folds into shapes, just like protein folding. So that has a very clear conclusion. In the 40s, telephone calls got worse with distance. Shannon digitized communication. For 10 years, the phone company fought about digital versus analog phones. The analog managers died, the digital generation took over, and we have the internet. They told me at the time that's how they won the management battles. This is the last great analog computer. Vannevar Bush made it at MIT. The longer you ran it, the worse the answer was. It was a room full of pulleys. Von Neumann digitized computation. We have Pentiums. However, the most advanced airplanes and chips are fundamentally analog in how they're made. The breakthrough in planes is instead of metal whacking at metal, we melt plastic. The fundamental process in chip making is you spread stuff around and you bake it. It's fundamentally analog in exactly the sense of von Neumann and Shannon. On the other hand, if you look at how the ribosome makes the proteins in your body, the molecular machine that's moving my arm and detecting light in your eye, it runs codes, it reads programs, it corrects errors in precisely the sense of Shannon and von Neumann. And the heart of that, the exponential, for me, that's the heart of today, is when you restore state, for a linear increase in resource, you get an exponential reduction in error. And that exponential reduction in error for a linear increase in resource is what gave us the internet and Pentiums. It doesn't apply to chips and airplanes, but all the technology I showed you is how you get there. So I'd say we had a digital revolution in communication, but we can declare success, we won. We had a digital revolution in computation. We can declare success, we won. The real impact of digitization coming is when you bring the programmability of the digital world to the physical world. That's not what happened in 1950 when Norbert Wiener connected a computer to a machine tool. It's when the computer becomes the machine tool. It's not when a program describes a thing. It's when the program becomes the thing that we bring the programmability of the digital world out to the physical world. Now, interestingly, there's enough people left, like Marvin Minsky, you can ask. John von Neumann and colleagues almost thought that thought in the 50s, but they didn't quite. Von Neumann was thinking about self-reproducing automata. Winograd and Cowan were thinking about reliable computation in the presence of noise. But they never put these together to code for construction, to digitize fabrication. But what they did get, and I think this picks up from the last discussion, is the reason von Neumann did this in this wonderful, not quite finished monograph on self-reproducing automata was he was thinking about the role of high and extremely high complication. He wanted to understand how to make stuff much more complex than we could any other way, how to create enormous complexity. And that's what led him to think about sort of feeling his way for connecting computation and construction. We're now at a point where we understand the implications in reliable construction with unreliable parts, and we're at the point where we can take this out of the world of simulation and bring it into the physical world. And so this is the path to create enormous complication. And I want to close with an observation that this is a 20-year roadmap to make the Star Trek replicator, the thing that makes anything. And we're going to get there as coded construction, embodied computation and materials. I spent many millions of your tax dollars doing that, thank you. And NSF said, when I spend that much money, you have to do outreach. And I didn't want to do like a website or a class, so I set up little field fab labs that are sort of like the PDPs. They're not yet the PCs, but kind of the PDPs of digital fab. And they spread all over the world, above the Arctic Circle, rural India, coast of South Africa. And people are doing wild things, making their own internet terminals and houses and energy devices. And what we're finding is the killer app of digital fabrication is personal fabrication. In the developed world, it means you get not what you can buy at Walmart, but what you can't buy at Walmart. And for the rest of the planet, it means technology gets created bottom up, top down. And I think in today's discussion, there's a lot of intangibles. To me, anybody making anything anywhere is enormously tangible. And once you start thinking about the digital revolution in fabrication is a huge, immediate coming impact of what we're talking about. And I talk about that if you're interested in the fab book I believe they have here. So with that, I'll thank you and take questions if there's time. One question? Who wants to be one question?
How does quantum affects this digital physical substrate? How much does awareness of and our participation in this hybrid man-machine?
Yeah. So the question is, what about quantum mechanics? I love quantum mechanics. I made among the world's first quantum computers. For the discussion here, quantum mechanics just isn't all that important. Your body is almost completely classical. It only uses quantum mechanics essentially in a few key places. It's largely classical. Quantum coherence lets you do some things you can do classically. The win of quantum mechanics is in certain special problems, either linear or exponential speedups. However, in what I showed you, there's a large number of exponential speedups that are much more applicable. So quantum mechanics is going to help pieces of what we're doing. But the subject of today, of this exponential scaling, largely doesn't need quantum mechanics. It helps in corners, but it's not the heart of the story. I think time is short. If there's time, 0 more questions?
Nope.
0 questions. Thank you.
Thank you, Neil.